All right, guys, let's talk about 9.1, Introduction to Probability. So first, let's talk about the definition of a sample space. So a sample space is a set of all possible outcomes of a random process or experiment. An event is a subset of a sample space. Okay, and we'll talk about that in just a second, give you a visual. This formula here is based off an event and the sample space. So S is a finite sample space in which all the outcomes are equally likely, and E is an event in S, then the probability of E, written this way, P of E, is equal to this. So the number of outcomes in E, the event, divided by the total number of outcomes in S. Okay, and let's do a quick example. For example, let's see here. A six-sided die. Right, so part A, find sample space S, just so you understand what it is. S will be equal to all the numbers that can come out on a single die, right? So that's S. B, let E be the event of an even number. So E would be a subset of S, meaning it's inside of S, which is equal to 2, 4, 6. Now let's say I asked, now if you see, just so you know, the notation meant the number of S. So if you see this N of S here, that is the number of elements in S. So that'll be 6. So there's 1, 2, 3, 4, 5, 6. Number of elements in E, by the way, it's going to be 3. So it's just a notational thing. So let's say we want to know what is the probability of E. All right, so the formula, if we shrink it down using this notation, would be equal to the number of elements in E divided by the number of elements in S. So what is the probability that it will be even, or that this event E will happen? So that will be 3 different ways it can happen, right? 1, 2, 3 out of the total. So that will be 50%, right? Which we kind of already knew. All right, so that's what sample space means, all the possible outcomes. That's what the event means, and this is what the notation means. Okay, and this is your formula that I written up here in more detail. Okay, so let's do probabilities for a deck of cards. So 52 cards. I'm hoping everyone's played with cards, but if not, you may want to pull out a picture of all the cards. But just in case, there's 52 cards, 4 of each type. It's 2 through 10, Jack, Queen, King, and Ace. Okay, so let's do number 1. What is a sample space of outcomes? So basically this would be, what is the sample space of outcomes? So S would be equal to the 2, the 3, the 4, right, all the way, and then there's 4 of each type. So it's going to be a ton of them. So just to keep it simple, we'll say that the number in S is equal to 52. Okay. Okay, now part B. what is the event that the chosen card is a black face card? So how many black faces are there? Well, there's let's see, 13 different types, right? There's ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there are 13 types. Half of them, half of the 52 cards are black. The other half are red. So black face would mean the suits. So Jack, Queen, King are considered to be faces. And there's 2 blacks for each type, right? So black face we'll call black face card would be Jack club, Jack spade, King club, King spade, Queen club, Queen spade. So 1, 2, 3, 4, 5, 6. So there's 6 elements in there. So if you were to say the number in blackface cards, that would be equal to 6. Okay, now C, what is the probability of choosing a black face card? All right, so probability of black face card is equal to the number of ways that can happen. So I'm going to abbreviate it BFC here over the number in the total sample space. So that will be 6 out of 52, which is about 11.5%. All right, let's do another one. Okay, let's do rolling a pair of dice. Running the sample space is kind of huge because there's 36 different ways. Let me show you a picture. So if you have a single dice, there's 6 ways. If you have 2 dice, you have 6 times 6 ways, which is 36. These are all the 36 outcomes right here. Okay, so 1, 1, 1, 2, whatever, right? Technically 2, 1 and 1, 2 are two different outcomes. You see that? Even though it feels like it's the same thing, one dice could be 2, and then the other dice could be 2, and then one dice could be 1, and the other dice could be 1. So we count those as two different outcomes, okay? So part A, what is the number of elements in S? Well, S is all the dice rolls, that'd be 36. Part B, what is the set, which we'll call E to make it shorter this time, set E, with outcomes on the dice that add up to, let's say, because this guy does 6, so we'll do 6. So I want to write these as pairs to make it simple. So E will be equal to kind of like coordinates. So to get a 6, I can get a 2 and a 4, or a 4 and a 2, right? I can also get a 5 and a 1, 1 and a 5. So 1 plus 5 is 6, 5 plus 1 is 6, 4 plus 2 is 6, 2 plus 4 is 6. Is there anything else? Oh yeah, 3, 3. 1, 2, 3, 4, 5. There are 5 elements. Now, let me double check this. The doubles are not counted as two different ones because both have to be 3, right? So there's no second event where if the other one's 3 and then the other one's 3, that's the same thing. So only these count as separate. 2, 4, 4, 2. So there are only 5. Okay. C, what is the probability of rolling a total of 6 on a pair of dice? Okay, so probability of E is what I'm asking, right? Will be the number of elements in E divided by the number of elements in the total, which will be 6 out of 36. Oh, I'm sorry, 5 out of 36. Right. Now, as a percent, we'd have to divide that and multiply by 100. Let me see. 5 divided by 36 times 100. And it's about 13.89%. Anyway, you can also count elements out of a list or out of an experiment by flipping coins or rolling dice. But anyway, that's all for 9.1.